Hi, I'm Dan Cortopassi. Welcome to Model Building Tips. In this episode, I'm going to talk about speed matching DCC equipped locomotives. I'm using N-scale as an example because that's what we've got set up here on the dining table, but the techniques apply just as well to any scale. Model train locomotives aren't all the same. I'm not just talking about the engine the model is supposed to represent, like a GP38 or a C44-9W. Mechanically, models are built with different motors and drivetrains. As a result, if you take any two random locomotives from your collection, chances are they won't run at the same speed at a given voltage. This is true even if you have two mechanically identical models, like these two engines from Kato. Both represent ES44AC locomotives, but right out of the box, the BNSF engine is a little faster than the CSX engine. One of the advantages of DCC control is that it gives us a way to deal with this. Locomotives that run on DCC need to have a DCC decoder. This is a little electronic gizmo that regulates the locomotive's behavior. In addition to speed and direction, decoders can also control lights and some make sounds. For this program, however, we're concerned with the locomotive's speed. DCC decoders have the ability to act like governors and can be used to limit the top speed of a locomotive as well as how the locomotive behaves throughout the speed range from stop to full throttle. When we talk about DCC speed matching, we're talking about calibrating two or more locomotives to run at the same speeds at any given throttle setting. This allows locomotives to run in multiple without fighting each other. This is especially important if you have a diesel-era railroad, as diesels are often seen in multiple unit sets. Most good quality decoders allow for two different methods to define how a locomotive responds to the throttle. One method uses 3 points to define the speed curve and the other uses 28. We'll talk more about that in a moment. First, a little background in case anyone isn't familiar with how DCC programming works. Decoders are programmed by assigning numerical values to configuration variables, or CVs. Each CV can hold a single number. The decoder then uses the numerical values stored in each CV to determine how to behave. There are CVs that control lighting, sounds, and many other things. For the 3-point method of speed matching, decoders use 3 important CVs. CV2 determines the minimum speed, which is the slowest speed the locomotive will sustain once the throttle is advanced above stop. CV5 defines the maximum speed, which is how fast the locomotive will run at full throttle. CV6 is the mid-range speed, which defines how fast the locomotive will run at half throttle. Not all decoders support all of these variables. Normally, I won't use a decoder that doesn't support at least CV2 and CV5. Two other important CVs are 3 and 4. CV3 controls the momentum for acceleration. CV4 controls the momentum for deceleration. Momentum is a way to simulate the inertia that real trains have due to their mass. A full-size train takes time to start and stop. The higher values set in the momentum CVs, the longer it will take the train to start and stop. I don't like seeing model trains lurch into motion and jerk to a stop unrealistically, so I prefer fairly high momentum settings. I should also mention CV29, which is a complex variable that uses a single number to configure several things at once. If you want to use a 28 CV speed curve instead of 3, then you'll need to figure out how to set CV29 to make the decoder do that. To understand CV29, you have to understand that digital devices like computers and DCC decoders represent numbers as strings of ones and zeros called bits. Each bit can either be on, represented by a 1, or off, represented by a 0. You could think of them like a bank of toggle switches. An 8-bit number is represented by 8 of these switches, numbered 0 through 7. We control these switches by adding numbers together to get a total that we then store in CV29. Adding 1 turns on bit 0. Adding 2 turns on bit 1. 4 turns on bit 2. 8 turns on bit 3. 16 turns on bit 4. And 32 turns on bit 5. Bits 6 and 7 aren't used in this case, so we don't need to worry about those. Bit 0 determines whether the engine will run forward or backwards when the throttle is set to move forward. If you add a 1 in here, then the engine will run opposite its normal direction of travel. That means that putting any odd number in CV29 will make the engine run opposite of its normal direction of travel. People typically use this if they installed the decoder with the motor wires reversed and don't want to physically change the wiring to fix it. Bit 1 is used to set speed steps, which is different from the speed curve. It can be 14 or 28/128. Typically, you want to set this to 28, which is done by adding 2 to the mix. Bit 2 is used to enable analog mode, which allows the decoder to run on a DC-powered track. Add 4 to enable this feature. If you leave this off, then your DCC locomotive won't run on a DC track with an old-school throttle. Bit 3 is for Railcom and isn't as heavily used, so we'll skip that one. Bit 4 is where you set the 28CV speed curve versus 3CV. Add 16 here if you want to use the 28CV curve. If you do that, then you'll need to program CVs 67 through 94 to set up your speed curve. Bit 5 determines whether the decoder uses a short or long address. Add 32 if you want to use a number above 128 as your decoder's address. So for example, if you want to set your decoder's address to 4449, then you would want to add 32 here. If your locomotive is number 8, then leave bit 5 at 0. Some software like the ESU Loc Programmer will set up CV29 for you, so it makes it a little easier. Some DCC throttles also have shortcuts. You can do it manually though. Let's say that we want our locomotive to run in the normal direction, so we'll add 0 to turn off bit 0. We want to use 28 speed steps, so we'll add 2 to turn on bit 1. We want to enable analog mode, so we add 4 to turn on bit 2. We'll skip bit 3, so add another 0. We want a 3CV speed curve, so we'll add 0 to turn off bit 4. And our locomotive's address in this case is 6920, so we'll add 32 to turn on bit 5. That leaves us with 0 plus 2 plus 4 plus 0 plus 0 plus 32, which equals 38. That's what we can program into CV29. For many decoders, 6 is the default setting for CV29, which are the same options with a short address, which by default is usually 3. Many DCC throttles allow you to program a long address and will reconfigure bit 5 for you. That means that most of the time you don't need to mess with CV29 directly, but I wanted to take a stab at explaining it anyway. Don't worry if this seems a little confusing. Like I said, most of the time you could ignore this unless you want to use the 28CV speed curve. As I mentioned, the DCC standard allows for different speed curve setups. In 3CV mode, the decoder has settings for minimum, maximum, and mid-range speed. In 28CV mode, there are settings for speeds at 28 different points along the speed curve. Most of the decoders I use default to the 3CV method. I've found that 3 speed CVs are usually sufficient. The decoder will interpolate the in-between values. I've used the 3CV mode for nearly all of my locomotives very successfully, so that's what I'm going to talk about in this program. Some people prefer the 28CV mode, but I find it to be too much work to do all that programming and not really necessary. There are different ways to determine a speed standard for your locomotives that you want to match. My method is to use one of my locomotives as the standard. It doesn't matter which one, really. Some people only speed match a certain group of engines that are always run together, but I like mine to all be standard. I like all my locomotives to be speed matched to each other so that I can run them in any combination that I like. In order to achieve that, I try to speed match my engines to the slowest locomotive that I have that I would want to use in a consist. In N, for example, I have this Atlas Shay that runs slower than most of my diesels. If I matched all of my engines to this one, they'd all be a little too slow. I don't foresee needing to use the Shay in a consist with diesels though, so I don't need to worry about that one. This Atlas SD60E, Norfolk Southern 6920, is my current standard N-scale locomotive. There are other approaches to speed matching. For example, some people like to calibrate their locomotives so that the numerical value on the throttle represents the speed of the engine in scale miles per hour. To do that, you'd need some kind of scale speed indicator so that you can measure the locomotive speed as it passes by. I've never used that method though, and I don't have anywhere to set something like that up right now. Also, distances on our layouts tend to be compressed, with towns much closer together than they are in real life. Even at a relatively slow speed, our model trains may arrive at the next town much more quickly than a real-world train that has to travel many miles at a higher speed. For this program, I'm going to focus on using a standard locomotive. As I mentioned, NS6920 is my standard locomotive. This Kato SD70M Union Pacific 4848 is the one that I want to speed match. Both of these models have ESU Loc Sound decoders installed. First, I'll set up both of my engines on one of my Digitrax throttles. I have 6920 on the left and 4848 on the right. Now I can add 6920 to a consist with 4848 as the lead engine. Let's see what happens when I open up the throttle. As you can see, 4848 is way faster. If you tried to run these engines coupled together like this, they would fight each other. I need to slow 4848 down so that it runs with 6920. I'll select 4848 on the throttle and then hit the program key to put the throttle into programming mode. I need to keep pressing program until the screen reads PO, which is ops mode or programming on the main. Now I can program CVs into the decoder while it's on a live track. First, I'll set CV2, the starting speed, to 1, which is what I use for Loc Sounds. Next, I'll set CV3, the momentum for acceleration, to 110, since I like a lot of momentum. This engine has a Loxound 4 series decoder, so the numeric values are a little different from the NMRA norm. I'll set CV4 deceleration to 90. Now I'm going to arbitrarily set CV5, the maximum speed, to 160. That's probably not where it'll end up, but I need to start somewhere, and now I know what the decoder is set to. I'll set CV6, the mid-range speed, to 80, which is half of 160. Let's run the engines again. I'll crank the throttle to 99, which is the maximum. 4848 is still way too fast. While it's running, I'll reprogram CV5 to 98. Better, but still fast. Let's try 86. That's getting better. The engines are running closer to the same speed now. Let's try 82. Now I need to watch for a while to see if 4848 is still catching up to 6920. After a few laps, 4848 has edged closer to 6920. The engines are within a hair's breadth of being coupled. Let's try 80. Now 4848 is starting to fall off the pace. It looks like 81 might be the winner. It's not always possible to match two different locomotives exactly. Eventually one of these will likely catch up with the other, but they're close enough now that they can be run in a consist without issues. But we're not quite done yet. If you recall, at the beginning I arbitrarily set CV6 to 80, which means that right now 4848's mid-range speed is almost the same as its max speed. Let's fix that by setting CV6 to 40. Now I'll dial the throttle back to 50 and watch what happens. It looks like 4848 is a tad slow. Let's reprogram CV6 to 41. If the engines are too far apart, sometimes I'll stop one until the other catches up. It's easier to see small differences in speed when the locomotives are closer together. It looks like 4848 is ever so slightly slower than 6920 at half throttle now, but probably not enough to matter. Now I want to check the momentum. In theory, the same numbers in two engines with the same type of decoder should produce the same amount of momentum, but I like to check anyway. I'll cut the throttle and watch the engines stop. If they're matched, then they'll come to a halt at the same time. If 4848 stops before 6920, then the value in CV4 would need to be increased. If it stops after 6920, then the value of CV4 would need to be reduced. The deceleration looks pretty good. Now let's check the acceleration. Just to make sure that any starting delay is factored out, I'll put the throttle on 1 for a moment until both engines start moving. Now I'll crank it up to max. If the value of CV3 is correct, then 4848 will accelerate at the same rate as 6920. If 4848 gets up to speed faster, the value of CV3 would need to be increased. If it lags, then the value of CV3 would need to be decreased. It looks like I guessed right on CV3. Let's cut the throttle and check deceleration one more time. It looks good. Now these two engines are matched and can be run in consist with one another without problems. I have been using this method for years and I've never found it necessary to mess around with more complicated 28 CV speed curves. Because the locomotives will interpolate the in-between values, both engines should now in theory go at the same speed at any given throttle setting. By the way, if your locomotive runs a little jerkily and you want to tweak any of the motor control CVs to smooth it out, do that before you speed match it. Sometimes changing the values in the motor control CVs will change the locomotive speed. So that's my basic technique for speed matching. Good luck with your modeling and thanks for watching.